what do we actually learn here? So we know that we've sought wave solutions of this form. So basically all the perturbations have this wave-like form. So e to the omega t plus ikz. And we want to see which grow, so which wavelengths grow, so which k, and which one grows fastest. Okay? And this has all of this information. So first off we see, so in order for them to grow, omega has to be positive, right? If omega is negative, it means that you get exponential decay of the perturbation. So you give it a kick and it dies, right? If omega is imaginary, it means that the wave will be neutrally stable. So basically it'll just go, but it won't grow. In order for the thing to grow, this has to have some positive real part. Okay? So from this you can see that that is going to be the case if this is positive, right? So for instability, so k are not less than 1. This thing's got to be positive. And that translates to lambda being greater than 2 pi r naught. Okay, so r naught is our initial radius. Okay? So for any disturbance with a wavelength which is greater than the circumference, perimeter, yes, circumference is going to go, right? So any long wavelength disturbance is going to grow. If it's small, it won't. Okay, so you can imagine a physical argument for this thing to go unstable. If it was, so imagine a really high frequency cutoff. That's going to be hugely energetically costly, right? It's not going to reduce the surface energy of the system. So those things are killed basically by surface tension. But these long wavelength instabilities are favored by surface tension. And you can say then, okay, well, we know that these are going to be unstable, and what is the actual fastest growing mode? So which is the, so this is saying, okay, all wavelengths will grow, but short wavelengths suppressed by surface tension. Okay. And the fastest growing mode is going to be that which maximizes, that with the maximum omega, and so you can just plot this and you see where it lies. Okay. So this is again the region of instability. And you see that the fastest growing mode comes in here. Okay, fastest growing mode. So real part omega is maximized for k r naught equals 0.697. For which the corresponding wavelength, so this is the fastest growing mode, and this is going to be the wavelength that you actually see, is around 9 times the undisturbed radius. Okay, so that's characteristic of Rayleigh Plateau. If you see an instability where the wavelength is around 10 times the radius of the thread, then you're going to know it's Rayleigh Plateau. Okay, and so given this, you can then sub back into here and find what the corresponding breakup time is. You can also get this just from a scaling argument, right? If you balance, you get the breakup time without the coefficient just by scaling. So we know that basically we don't have viscosity here, so we know it's a balance of inertia and surface tension, sigma over R naught, right? And so we say, so if we say U is order R naught over tau, then we get rho R naught squared over tau squared sigma over R naught. Then it should give us this capillary time. Yes, R, so it's rho yeah, so rho R naught cubed over sigma to the 1/2. Okay. So that's basically whenever you have a situation where surface tension is driving the flow and it's being resisted by the fluid inertia, this is the time scale. Okay? So this is basically the capillary time. That's how long a fluid is going to take to deform in response to curvature forces resisted by inertia. Okay, so that gives you the capillary time, and then from this equation you actually get the coefficient. So the coefficient is about 3 times that. Right? Okay, so that really tells us everything we need to know. So there you have the possibility of an instability for all long wavelength disturbances, but one of them is going to grow faster. And because they're growing exponentially, the one with the largest exponential growth rate is going to be the one you actually see. So this rationalizes the breakup, which you see in many situations. In particular, this video we saw, I think we can see, we'll be able to spot some Rayleigh Plateau here. This paint is not a Newtonian fluid, so there can be other effects. But if you look at the pinch off, yeah, you can see a factor of 10 coming in there. And I'll show you water. Water, it's very clearly a factor of 10. So there are additional complicating factors here. In particular, viscosity is one. So we just saw the inviscid calculation where you get this very nice result of 10 times the radius. So there is another, if you consider viscosity, then there's this additional dimensionless group, which is basically curvature to viscosity. Right? So, and there, things are going to change. And as we can see in that video, I think viscosity was probably coming into play as well as non-Newtonian effects. But you have the relevant time now is not, if you're at low Reynolds number, the relevant pinch-off time is not set by the fluid inertia, but it's resisted principally by viscosity. So you have instability on this time scale, and it turns out that in this viscous limit, the wavelength increases with viscosity. It's kind of it's a relatively nasty. If you thought that last calculation was nasty, the viscous one is even worse. So, okay, I'll just show you some real classic Rayleigh Plateau, and then remind you that this is a stability, an instability which one really sees everywhere one looks. So, okay, but this is certainly I can't hit larger. It doesn't fit. Okay. All right. Let's just look at it in small then. But this is basically a fluid jet coming down. I think it's water, but you can see that long wavelength disturbance developing, and that's basically the one that we've just predicted. So that's has about 10 times the wavelength, and then you get the subsidiary pinch-offs, but the basic mechanism is the same. Again, with linear stability theory, all you're doing is predicting the first disturbance. After that, you have to look at nonlinear theory. But it's quite remarkable how well linear theory works in general. It works for a whole. It'll generally give you that first. The wavelength of the first instability, and then again things are more complicated. Okay, and so yeah, I think this is water. Let's try another one. Yeah, and if you use other fluids, like so non-Newtonian fluids or more viscous fluids, things get more complicated. This one's not looking too Newtonian. Well, it does say water jet. It must still be water, but it's looking a little bit patchy. Maybe it's dirty water and surfactants come into play, because those will also change. But there again, you can still see the factor of 10. And then one can also, one sees, whoa, that's too large. Whoa. Well, so it's a very generic instability. And you can see manifestations of it basically in any free surface flow. Whenever there's a flow dominated by I need to get out of this to get my... Okay, so here we go. The last. Okay, so here we see a jet skipping off the surface. Okay, so this is a silicon oil. Because of the relative motion between the jet and the bath, there's an air layer between the two, which keeps it from merging. So basically skips off. But then at the end, this is always Rayleigh Plateau happening there. So you're sort of seeing what's happening there at the end of the kitchen tap when you turn it on. Okay, so we're going to look at so we're going to look at this. Actually, I'll save that for later. Okay, so let's look at a few more applications of this. So, a very simple experiment that you can do in in the kitchen, in the bathroom, you basically turn on a jet. So this is about, this is millimeter grid here. So you can see this is about 2 millimeters across. So if you just turn the jet on a little bit, and then if you hold your finger beneath the stream, you'll see a field of waves. So this is actually hitting a bath. It's the same business. But if you just hold your finger in a stream of water, you'll see that there will be a field of standing waves. So actually standing on the jet just above your finger. And the reason you see them is that they're moving, they're the waves which have the wave speed which matches that of the incident jet. So they're going up at exactly the same speed as the jet is coming down, so they appear to be stationary on the jet, right? And we know what the wave speed is because we've just solved the dispersion relation, right? We know what omega is as a function of k, what the frequency is a function of the wave number, and the wave speed is simply given by omega over k, right? That being the case, we can find the wave number which, for which this relation holds, right? And that's going to be the wavelength which we see on the jet, okay? So again, we use this, our dispersion relation, and this, so if we're given the jet speed, and we can, the calculation we did at the beginning of class will tell you how fast the jet is going as a function of distance from the orifice, so basically where you put your finger, and as you'll see that as you move your finger up and down, so change the local jet speed, the wavelength will change, okay? So this is a straightforward application of the two problems that we've solved today. Okay, and we've yesterday we learned about surfactants, and so how does the picture change so instead of here we had the thing hitting a bath. So again, the easiest way to do this is turn on your jet on and then have a glass of water. Basically move it up and down. You'll be able to see these. So what happens if you put now soap in your glass of water? So if you put soap in, then there's a surface tension gradient, and what you'll see actually is, so that if it's pure water coming into soapy water, then the surface tension is higher here in the jet relative to the bath surface, right? So then you have a Marangoni stress which pulls fluid upwards. So you have this region here where there's a Marangoni stress, and if you just observe it casually, if you blow chalk dust on it, then the chalk dust will stick to this surface. So this is actually stagnant. So the jet is then entering the reservoir as if through a rigid pipe. Okay? And so, and again, it's because you have this gradient in surface tension along here, which gives rise to a tangential stress which balances the viscous stresses of the impinging jet. Okay? And so how can you predict the length of this? So again, upstream, so you basically then have this disturbance which is now acting here. So upstream you still have these waves as predicted on the previous slide, but now we have this pipe region where the free surface is rigid. So how can we predict that? We know that there has to be a balance between the viscous stress and the Marangoni stress. So good to get what we need is an estimate of the viscous stress. Okay, so we need to know, basically we need to have an estimate of the boundary layer thickness. And this, have you guys done Blasius boundary layers? Probably not. But if you have, basically, if you have a plate in a flow, so it's a plate in a uniform flow, then you basically get a boundary layer which grows up. It grows up like square root. If this is x, then delta goes as square root of x. And the coefficient is given here. Okay? So basically depends on the, you're basically, this rigid surface is acting as a source of vorticity, and so the vorticity is diffusing up into the overlying flow. And so you can get this shape by balancing convection, advection, and diffusion. Okay? So this is the Blasius boundary layer. And so from this, you can make an estimate of how thick the boundary layer is and what the viscous stresses are. And so by balancing them, you can get an estimate for the for the height of the pipe. So you can see that this pipe height, as you expected, increases with the surface tension difference. So the larger the surface tension difference, the larger the Marangoni stress, and the longer this pipe. And then as it decreases with increasing jet speed and viscous stress, because if the flow is too large, it will dominate. The viscous stresses will compress this pipe into a small region. There's an example, but this is another example where you're getting the suppression of waves by the surfactants, right? So if you remember that the cartoon I showed of wind blowing over a puddle, it's effectively the same thing, right? You basically have this region here where the surfactant is confined to the pipe, just like when you have wind blowing over the puddle, the surfactants are swept to the back of the puddle, then you have a wavy region upstream, right?
It looks as though the pipe gets thinner right before it hits the water. I'm not sure if it's...
It's thinner there? There? Yeah. Yeah, I don't know. I don't understand that. I never understood that. Good question. Okay. So, and here's another... here's another flow in which dominated by surface. And so we've seen this before, but this is the Coalescence Cascade, where you have the drop coalescing bit by bit. It's decreasing in size actually by a factor of 2 with each coalescence, and then finally it dies. And so it was my first student who finally solved this problem. It required doing numerics, which is something that I never do. But, he did a very nice job. So he found that the question is, why doesn't it just merge completely, right? And so he showed that if you when the thing coalesces, so it's basically sitting on the surface with an air layer, right, for a while, and then finally you initiate coalescence, and when you do, you have this violent motion. So basically this air film retracts, so you get this very quick motion, and this excites waves, and the waves then sweep upwards and they transfer momentum to the drop, and so it jumps. Okay? So that's what's responsible for actually lifting off. And you can ask how this would change with, so imagine now we have pure water on alcohol. So on alcohol we know the surface tension is lower. And so we expect something sort of fluid pipe-like. We expect there to be Marangoni stresses which alter the flow. Okay? So let's see what happens. So here's pure water on alcohol. So we know that the surface tension is higher on the drop than the bath. So there it coalesces immediately, and you can see there's basically a jet shot up, right? It's because there's a Marangoni stress. The surface tension is higher at the top of the drop than the bottom as soon as it merges, right? So you get basically get this intense Marangoni stress which pulls fluid upwards, and so if this was just pure water, it's basically, the difference is, again, as soon as it merges, you have high surface tension here relative to here, so you get this jet, so you actually see the fluid being pulled upwards. Okay, and so in the next, I'm going to look now at a couple of variants on Rayleigh Plateau, and we can see them here. Okay, so let's just change the geometry a bit. Now let's look at the instability of a fluid layer on a cylindrical substrate. Okay, so this is, so you see what happened there? We basically wet the cylinder, and then you can see the instability. And this is so this is actually relevant geometry in a lot of industrial applications. For example, wetting, they coat fiber optic cables. Right? So you're basically coating a cable. You want to coat it with a water repellent fluid, but you don't want the instability to leave bare parts on the wire. So this is actually, and so you can ask what's the most relevant pulling speed, right? If you pull it too fast, there's a question of how much fluid you actually place on the fiber, and there's also the element, the question of whether you get an instability, how long it's going to take. And that'll depend, of course, on the viscosity as well, if viscosity is important. And here is, so here we go again. Slightly slowed down version. But you can still see that the wavelength is about 10 times, right? And so here's another twist on it, which is the, so now we have a cylinder, and we pump air. So we have a cylinder full of fluid, and then we pump air through. And so then you have a layer of fluid on the walls of the cylinder, and these will eventually, so those are these, and you can see them going unstable. Right, so you get the geometry. Start off with this is like if you leave a tube in the lab, and then you pump air through. So you start off with a cylindrical shell of fluid, and that then pinches off in through a mechanism related to Rayleigh Plateau. Again, the system is trying to minimize its surface energy. So that means, in this case, an instability with this wavelength. And you'll see this if you ever leave a tube lying around the lab, you come back the next day and you always have bubbles of exactly the same size. And it's because of this instability. Okay, so okay, so I'm just trying to decide on whether I want to embark on more algebra today. Any questions? Come on. Yeah, maybe I'll just set up this problem. Unless you have some probing questions. Oh, are you going to hand in your problem sets? Yeah? Okay. All right. So much algebra today.
That's the problem with CMLR. If you are like in zero gravity, you remove the gravity of the particle.
Pardon me? Yep.
If you forget gravity, if you
Yeah,
are
yeah.
in zero gravity,
Yeah.
do you still have the same?
Yeah, gravity is not playing a role in any of this. So gravity will, in general,
Because it's jet is horizontal. That's why.
right on this one, for example. Well, so I mean, if gravity is important, then the lower layer will be thicker than the top layer, say, right? So it'll come in. But if as long as if this is a small tube, then you won't have to worry about it, right? So if you have something millimetric in scale. Okay. I I'm just thinking we've got 10 minutes left. I'm going to have to, I can't possibly get through this calculation. I'm just going to tell you what we're going to do. We're just going to look at this. So we start off with a cylinder. So you start off with a thickness h naught, and you want to predict the wavelength of instability. Try that again. Okay, what's going to be the most unstable mode? Okay, so if we have this once we have this perturbed state, the mean is actually not equal to h naught. We can define the mean thickness This is just a preliminary calculation, but we'll get save some of the pain next time. Epsilon plus qx. Let's call it kx. Okay, so then continuity. Okay, this is saying that the volume in this case is the same as the volume in this case. Okay, what we're going to do here is just calculate what h star is, and then we can use that next class. Okay. Almost there. Okay, so this is saying that our average perturbed height, thickness on the cylinder has this form. And this, so it's always less than h naught. Which suggests instability. It's suggesting that any wavelength disturbance is going to decrease the surface energy. This is not, so this suggests instability, but we're going to need to when do we actually decrease the surface energy? Of course, decreasing the surface energy means decreasing the surface area, so we're going to actually have to work through it a little bit. To resist instability? Yes, true. But then they also, is like if you're pulling a fiber out of a fluid, that actually also creates additional forces, so it'll change the thickness of the layer in place. Okay, so when is the surface area decreased? So that's really the question we want to answer. And so we need to know what this is. Let's stop for now. Way too much algebra today. I'll give you guys another problem set maybe on Friday.